We're recording, right? Okay, yeah, great. We're recording. First thing of the second semester, folks. Here we go. We're going to talk about the overview for slope intercept and various other things like that. Just as a review, what's going on in this particular chapter, we're talking about straight lines, constant slopes, constant rate of change. That's stuff we learned about in the last section, and we're just going to find ways to describe them. So I just want you to understand that there are some rules about how to describe a line, and they come from actually geometry. So if I put in 2 points, let's go with the point 0, 2, 0, 2, 2, there, and the point we'll go with 3, there. All right, so I have these 2 points I just graphed. And what we're going to talk about is how to describe a specific line. The reason I picked 2 points is because there's only one possible line. This is a rule of mathematics. It's a postulate that you will learn next year in geometry. There's only one possible line that could go through those 2 points. I could have a line that goes down, but that wouldn't go through both of the points. It might go through one of them, but not the other one. It could go up, but it has to go up at just the right steepness so that it goes through both of those lines. And what we're going to describe, we're going to find our rules to describe lines. So the neat thing about this, since there's only one possible line that goes through there, that means we can describe lines as unique things. We can describe them uniquely. So if I use y equals mx plus b, which is our first thing we're going to review, 2x plus 1. Notice the green line I just graphed does not go through these 2 points. But if I scoot it up 1, now it goes through one of the points. Now I have to change its steepness so it goes through the blue point over there. So I would have to change this number right here to, I don't know, I could change it to 2/3. And now we've got a line that goes through both of those points. That's the only possible line that goes through those 2 points. This formula, if I write y equals mx plus b in this specific way, this is the only line, the only thing that represents this. If I change any of these numbers, it changes how steep the line is, and it makes it not go through that point. So that's the cool thing. It doesn't matter which number I change, it will alter where the line is. So basically this entire chapter is ways to describe lines uniquely. All right, so if I tell you, hey, here's a line, you should be able to, by the end of this chapter, to write a function for it. And if I give you a function, you should be able to say, oh yeah, that's this line, because it only represents one possible line. And that's what we're talking about, uniquely describing lines. Now we will learn other ways to describe lines. This is the first one. This is the one that you probably recognize from 8th grade, but we will also do 2 other forms called standard form and point slope form. This one called slope intercept form. And we'll talk about that later. But let's get to the assignment. I just wanted you to understand the basic goals of this assignment of this whole chapter, is to be able to go between this, y equals something, to this, a line, and realize that they're the same thing. This doesn't represent any other line, and this line doesn't represent any other form of this, or of this form of the equation, any other version of this form, any other set of numbers. So we will talk about that, but for now, let's get to the assignment. Leave this. Okay. So this is the assignment. The first assignment you have is called Overview. When you click on here, you should have an assignment like this. Notice it's page 131. I'm trying to be good about putting that into the assignment. And let's talk about this. Oh my gosh, I forgot to go in Agile Mind. Sorry to waste a tiny bit of time. You're getting to watch me not get into the computer the first time. Yay. Okay. So my course is algebra. Here's where we are. We've done 1, 2, 3, and 4. We're on 5 now. I'm going to try to get going. Here's what we have. Terrence and his friend. Oh, Terrence is our skateboarding person from earlier. We're going to play this animation and we're going to investigate some things. So Terrence is pulling her with a rope and she is moving forward. Looks like she's moving forward at a constant rate. All right. So we got this information. At the beginning, she's right in front of the thing. By the end of 10 seconds, she's moved Oh, about 4 feet, hasn't she? Yeah. And they make a graph of it, and look at that, it makes a straight line. Now we learned straight line means that we're going at the same speed. We're not speeding up, we're not slowing down. She's going nice and slowly. It's not the best it could have been. Let's try that again. Let's start out at about 0.7 right here. Notice she's not speeding up. She's not slowing down. She's just coasting at the same speed constantly. Remember, if something has a straight line, that means it has a constant speed of something. Some change is constant. Like that could mean they save the same amount of money every week, or that could mean they go the same amount of inches per second. But something is staying the same, and that's why the line stays straight. If that rate of change were changing, if they started saving more money, or she started going faster, the line would go steeper. So that's a great way to tell that you're going to deal with something that's a straight line. Some change is occurring at a constant rate. All right, so we have all of this. We're going to talk about, yes, the constant rate is represented by slope of the line that you made. And we were just talking about that. She's going at a constant speed, and that makes a line with a certain steepness. If she was going a faster speed, then the line would be steeper, like this. Oops. Like this. Watch, I go faster. That makes a steeper line. She's going too fast. So that's what we're talking about. Slope has to do with the steepness of this line, and it also has to do with her speed in this case. Let's see what this shows. Oh yeah, we can look at how much each of these changes by. Now notice we did this in the past too. Oops, this changes by 1 every time, doesn't it? Oops. Actually, you know what? We're going to go fill this out because that's what we're supposed to be filling out anyway. There it is right there. Okay. So how do you decide where Teresa should begin skateboarding? Well, at the beginning, at 0, this is time. At time, 0 in seconds. She has to be just a little bit less than 1 foot. It said 0.7, right? That was the first number in the graph right here. So I knew I had to start just a little bit less, around 0.7 feet from the thing. So we could say the starting point is where time equals 0. 0.07. 0.7 says she starts 0.7 feet from the motion detector. So that's a way we could tell where to start her. Now we've already done this kind of stuff. So I hope that for anyone who's jumping into this class, this is not too complicated. Let me just remind you though, when we talk about motion detector and all this stuff, you might as well understand what we're talking about. So in this problem, especially if you're new, you'll notice there's her and there's him, and he was pulling her on the thing. This thing over here on the left side is the motion detector. So it keeps track of how close to it she is. So now she's far away from it. Now she's close to it. Now she's about halfway. Now she's far away again. You can see the blue line moves to show how far away from this she is. And that's what we're talking about. So how far away is she? She starts out pretty close and she gets further and further away. And what's true about the rate at which you must drag the skateboarder? The rate must be constant. The rate speed of the skateboard must be constant. Or the line will not be straight. Okay, now we're going to calculate the differences. Notice this one right here, this goes up by 1 every time. right? So I'm just going to draw ones in here. 1, because we're counting the seconds in ones. And I don't mind if you do this. It's always 1. That's fine. Okay, on the other side, this goes up by from 0.7 to 1.1. Now, I like to think of this, just so you understand, you can do this type of math really fast. The points are just to keep track of what's going on, or where the lines, how to line up these numbers. That's what decimal points do. They just tell us how to line up the numbers, really. So if I just think of this as 7 and 11 and 15 and 19 and 23, and I just remember to keep the decimal point, it works. From 7 up to 11 is 4, only this is 0.4. And from 11 up to 15 is 4, only this is 0.4. So you'll notice that these go up by 0.4s every time. Okay, so what are we going to say? The y value, or sorry, x is our, what is our x? Well, it's time, because that's on the x-axis. That'll do. It's a little bit wordy, but it'll work. So we notice that x goes up by 1s each time. Y, on the other hand, now we've been talking about speed. That's the steepness of the line. But really what the y is keeping track of is distance. That's why it says distance. How far she is from, or the skateboard or whatever, is from that motion detector. So distance. Not 0.1, I want 0.4, right? It comes with 5.4 feet. There's plenty of space. Okay, yep. I guess I'm going to put in there. So what we notice is the x's count up by the same amount every time, the y's count up by the same amount every time. That is what makes this a straight line. If the x's or the y's change in how much they're going, if this changes, but that does not, if one changes by a different amount, but the other stays the same, then you're going to have a line that bends every single time for the rest of life, okay? So remember that. As long as it continues to go up by the same amount on both sides, you got yourself a straight line. That's how we get our slope. Now, the x value of the point at which the graph, at which it crosses the y-axis. That's an important thing to note. What is this called right here, where a graph crosses the y-axis? That is called the, I'm just going to type it in here. Think about it. You probably know the y-intercept. Well, I should actually have that be red so you can see it. There. Okay, so as gas flows into Alex's tank, oh, now we're filling up a tank. All right. Well, maybe we should double check to see this. Now, honestly, these problems are pretty straightforward. We're done filling and we're done skateboarding. Let's see if we can find a tank. Look at that. Now, we're going to get to this. Oh, they're talking about slope and intercept. That's interesting. Maybe I didn't read the instructions well. Let me double check. But here's what we notice. This goes up by 1s. That goes up by 0.4s, right? And we're going to use this to be able to write an equation that describes what's going on there. The equation they have is y equals 0.4x plus 0.7. That's very similar to what I had at the very beginning of this assignment when I was trying to show you some other line. Okay, this is y equals mx plus b, which you may or may not have learned about. So, interesting. Okay, so the rate of the line is, well, remember we do y divided by x. So we always do 0.4 divided by 1. Oops, I did 0.04. 0.4 feet per second. Okay, we shouldn't say unit. That's why we say unit. Okay, so what are we going to talk about here? Okay, so this right here, this is very, very, very important. I'm going to make it bold or something. I don't know. I guess I can't, but that's okay. This right here, we just found the slope, which is the rate. Rate is slope. All right. All right, they're the same thing. So when I look at this, it goes up about 0.4 of a square for every 1 square it goes over. It does, 4/10 of a square up. For every 10 squares it moves over, it goes up 4 squares. 4/10 of a square every single time. So that's right there. This is very important for you to understand. Slope is rate. Rate is slope. Y, how much y changes divided by how much x changes will always tell you how steep a line is, which is the rate. Now remember, way back when we talked about being able to change how steep something looks by changing the scale here or here. Well, the cool thing is, I'm not looking at the scale. I'm looking at the actual amount that x and y changes, 1 and 0.4. So it doesn't really matter what the scale on the graph is at that point. It's just going to be, I think I'm getting rid of something I don't want to. It doesn't matter what the scale of the graph is, because I'm keeping track of this using numbers. So this will always work. How much y changes divided by how much x changes, and we'll get to that in a moment. Okay, so Alex's gas tank now is flowing at a steady rate. To explain the relationship between the height of the float in Alex's gas tank and the number of gallons in the tank. What type of graph would model that relationship between the heights of the float in the tank and the number of gallons of gas in the tank? Okay, well, let's look at what they're talking about. We got lots of great, here's Alex. Okay, he's driving home. Fortunately, he passed a gas station. He pulls in to fill the tank. He lets the pump run. His car has a 12-gallon fuel tank, but he notices the pump shows that he has put in not quite 11 gallons of gasoline. So he tries to add more, but it runs over. Oh no, it gets all over his hands. Remember, don't top it off. It's fine. Okay, so reading the fuel gauge correct. The reading on the fuel gauge is correlated to the height of the float inside the fuel tank. Play the animation to see this. Okay, let's play the animation. Animation. Oh, here we are. Okay. Notice it's empty. This is the tank, I guess, and this is a little float. And what happens is, as the gas fills the tank, this thing floats, and that makes this change. Now, is this the way it always works? Notice it's more full, which floats this little float box thing, which brings this higher to show that there's more gas in the tank. Oh, and there you go. And that, if you ever wondered, is why sometimes when things are leaning a certain way, the float doesn't float as much, because the gas moves to a different part of the tank, not underneath the float. But of course, this is a little bit more old school. Now we use electronic things. But here's what we notice. He's been filling this thing up. The height of the float, as the float goes up, so does the number of gallons in the tank. That means that they're related. Oh, they're not directly proportional or anything, because it doesn't go through 0, 0, but as one goes up, the other goes up. Okay? That's important. As one goes up, the other goes up. That's about as important as far as we need to go down that road. Okay, so that's pretty straightforward, I hope. Now here's the thing we notice. This, he starts out with just over a gallon in there, and he gets up to 12 gallons. He didn't put in the full gallons because there's a tiny bit in there. But as this goes up, so does that. Do they go up at a proportional rate? Or do they, like, does one go up more faster than the other? It looks like it does, because it takes 10 seconds, and he gets in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and a tiny bit more, just a little bit more than 10 gallons of gas, right? So that's interesting to think about. Notice the graph on there. This is the function model's relationship between the number of gallons of gas and float that the y-intercept has is at 1.5. This states that what? Well, that means that the amount of gas in the tank was higher than he thought. The float, on the other hand, said that he was empty. So what's happening? This setup was telling him he was on empty, even though he actually had a tiny bit of gas in the tank. That's actually very common with cars, because people who make cars know that, honestly, people are kind of dumb sometimes and they wait a little too long to fill the tank. So they kind of often will set up a float like this so that when you run out of gas, you're not really out of gas. So you have a chance to get to the gas station, because people run out of gas all the time that way. All right. So what do we notice from this? The gas tank, the float says the gas tank is empty, even though there's 1.5 gallons in there. That's very important to note. And that means that it goes up by a little bit steeper than it should. It goes up a tiny bit more than it goes over. So even though you're filling it with 10 gallons, it's actually filling it with a little bit, or sorry, even though the float says you've gone up 10 gallons, you're actually putting a little bit more in because of its height. I'm going crazy. Sorry. The height changes by 10 inches. The gallons, you're only actually putting in about 10.5 gallons, not 12. All right, let's talk about this. What do we notice? Well, we notice that as the float gets higher, the gauge goes up toward full. See if we're answering the question. Explain the relationship between the height of the float, yeah, and Alex's gas tank, and the number of gallons in the tank. Oh, you know what? I actually said between the gauge. Why are they showing the outlaw? Okay. Let's answer the question correctly. The tank gets filled with gas, the float rises higher above the bottom of the tank. This causes the gauge to move toward full. Okay, what type of graph would that make? Well, for every 1 foot, one thing changes, the other thing changes by a certain amount, right? So we got a straight line, right? And that's because consistently, as this goes up a certain amount, that changes by a certain amount. So if this only changed by 1 inch and that changed by 1 chunk, and then the next inch this changed by 2 chunks, that would not be great. No, it's consistent. The amount that the float floats affects the amount that this moves the same amount consistently, constantly. And so this would make a straight line. This, since the change in since it's consistent, oops, I missed an S. The graph will, oh, how did I get black? It's so weird when that happens. The graph should be a straight line. Is a constant rate. Okay, here's a graph modeling a relationship there. Okay, the height of the float in Alex's tank and the number of gallons of gas in the tank. Okay, so here it is. What's the y-intercept? Y-intercept is right here. It's 1.5. There. Float is at 0, so the float's saying there's nothing in the tank. The gauge says it's empty. There's still down here 1.5 gallons of gas in the tank. What does the slope explain? What's the slope mean in this situation? Okay, so here's our slope. For every one we go over here, we go up by something. Now here's the tricky thing. Can I actually figure that out from looking at the graph? Not really. So how can I figure out how far it goes over and how far it goes up? It's a very important thing to remember. This is why you learn how to simplify fractions too. Rather than looking at every little chunk, because this doesn't really tell me. It doesn't give me any information. I can ask myself, well, how far does it move all together? It moves 10, right? And it moves up from 1.5 to 12, which is a total of 10.5. All right. Okay, so what does that mean? The slope of the graph, remember, change in y divided by change in x. That's always what happens. Is, well, that's 10.5 divided by 10. 10.5 divided by 10. Or 1.05 or 1.05. Sorry about that. Gallons per inch. That means, well, it helps to have the gallons per inch written in there because I always have the change in y, that's how much gallons changes, divided by change in x, that's how much the float inches changes. What does that mean? Well, for every 1 inch, now, this is why it's very useful to learn your fractions and learn how to do things with larger fractions. We could figure out, oh yeah, that goes up by 1 and then a tiny bit more, but how much more? 0.05. Could you have guessed that by looking? No. So it's much easier to look at data we know. We know that it gets up to 12 gallons because it overflowed its full tank. And this went up 10 inches. So That's my two numbers I'm going to use. It went up 10.5 gallons was 10 inches that the float went up inside the tank. And that's the trick. Okay, now we're going to do reinforcing, which doesn't mean which should go faster. Salazar has a new office manager and wants to make long-term plans for ordering supplies. He's been tracking the number of pencils in the pencil cabinet, supply cabinet. What's the rate of change exhibited in the data? Okay, now watch out. Notice this goes up by 1, but then it goes up by 2, and it goes up by 1, and it goes up by 2. He's not checking every single day. So if people are using things at a constant rate, we can expect to use twice as much during these 2 days as we did during the first 1 day. Okay, that's why we always have to check both sides. If this goes up by different amounts, we can expect different amounts of pencils to be missing. So what's going on here? They used 3 pencils the first day. The next day they used, let's see, from 50 down to 44. That's down 6 pencils. Oh, I'm going to put a minus because it went down. Down 6 pencils. Okay, and then we lose another 3 pencils here. And now we lose another 6 pencils. Notice, we talked about all these curvy graphs at the end of last chapter. This is not a curvy graph. What do we notice? Well, when 1 day goes by, they lose 3 pencils. When 2 days goes by, they lose 6 pencils. Is that consistent? Yeah, that's actually quite consistent. I can figure out how much I could do slope. And I could say, hey, so on day 1, 3 pencils, we lose 3 pencils. That's our y on day 1. Or -6 over day 2. For 2 days, we lose 6 pencils. Either way, you get the rate / slope is -3. This means they use 3 pencils each day. And that's the cool thing. This can change, but as long as that changes, as long as I keep my numbers lined up and I compare 1 day with 3 pencils, 2 days with 6 pencils, I always get the same thing, -3. They use 3 pencils a day. All right, bakery shop. At a bakery shop, each baker works at his own speed, making the same number of cakes each day. Marissa makes 28 cakes in 2 weeks. Carlos makes 60 cakes in 20 days. And Shelby makes 5 cakes in 2 days. When the shop owner graphs the relationships between the number of cakes made, who has the steepest graph and why? Okay, so this is why we think of slopes as fractions. I love myself a good fraction. So, what are we saying? Let's really quickly write a fraction. So remember, slope is change in y over change in x. I'm going to put this little thing here so that everyone knows that we're talking about change. Remember, that little triangle always means change. If you're in science class, it means change. It's called delta. It's just the letter D in Greek. Okay, so we've got that. Well, let me make that x look better. All right, so let's look at this. We have Marissa, M. Let's see, x is the independent variable. So the number of cakes you make depends on how much time you have. Notice we're doing some in days and some in weeks. I'm going to keep them all as days. So it takes Marissa 14 days to make 28 cakes. 14 days, 28 cakes. What does that mean? She makes 2 cakes a day. All right, Carlos makes 60 cakes in 20 days. So Carlos, 60 cakes in 20 days. He made a lot more cakes, but he has more time, right? But if I look at that, that actually simplifies to 3. So if I can write these as fractions, the fractions kind of resolve the issue. I don't have to do all of the work in my head. I can just say, oh yeah, he makes 3 cakes a day. And Shelby, on the other hand, makes 5 cakes in 2 days. 5 cakes, 2 days. Well, 5 divided by 2 is 2.5. So she makes about 2.5 cakes per day. Carissa makes 2 cakes per day. Carlos makes 3 cakes per day. Colby makes 2.5 cakes. And there you go. Okay, but we have to answer the question, which one will be steepest? Well, if you remember, with this, all of these, we talked about steepness being the speed of something, right? So steepness, a steeper thing means that the skateboard is going steeper. If this was steeper, that would mean that they're filling up. Well, it actually means something completely different because there's no time on the bottom. It would mean that each float means more gallons of gas in the tank, but that's fun. Here, if the number were bigger, it would mean they lose more pencils per day. So the steepness has to do with the speed. The question is, who makes the cakes fastest? That's going to be the steepest graph. And that would be Carlos. So Carlos would have the steepest graph slope. That is because rate he makes cakes at the fastest rate. Right, and that's what we're going to have for this assignment. So make sure you turn this in. I hope that this is really easy and you're just rolling your eyes because it's so simple, because this is just review, okay? I want you to understand we're going to be talking about y equals mx plus b, okay, in the next section. M is going to be the steepness. Or the slope, or the rate. B is going to be the y-intercept. The starting amount. Okay, so we've talked about that a lot. Let's see how it goes in the next section. All right, turn it in. Have a wonderful day, folks. And stop recording.